Good morning, everyone, and welcome to this keynote. It's a great pleasure and honor to introduce Lise Getoor, who is our keynote speaker for today's morning. Lise has received her master's from UC Berkeley and her PhD from Stanford. She was a faculty at University of Maryland until 2013. And since 2013, she has been at UC Santa Cruz. I had the great pleasure of sharing an office right next to hers and seeing her energy and her enthusiasm. Lisa has had a very long and distinguished career, but in very typical Lisa style, she told me that I have to keep it short so that she can focus on the substance. But I'll just briefly mention that she has had numerous Best Paper Awards, Best Student Paper Awards. She has also served on the advisory boards of institutes and committees. She has been an elected fellow of the AAAI. This is just a small sampling of the achievements. And I don't have a lot of time to talk about this, but without further ado, I'd like to invite Lisa to deliver the keynote. Thank you very much.
Great. So thank you very much, and it's a big pleasure and honor to be here. In this talk, I'm going to be talking about structure, and I'm going to be talking about structure both in the inputs to our machine learning algorithms and also in the outputs of our machine learning algorithms. So what do I mean by structure in the inputs? I simply mean that, all this crazy data that we're being inundated with oftentimes has a lot of structure. So it's multimodal, there's different kinds of entities, it's multi-relational, there's all kinds of different links between things. There's other kinds of structure, spatiotemporal, and so on. And I think there's a real opportunity to have machine learning algorithms that can exploit the structure that's in the input. On the other hand, there's also oftentimes structure in the output. So think of the classic kind of structured prediction kinds of problems in natural language processing, in computer vision, in computational biology. And I'm going to be talking about some others later in the talk in computational social science, knowledge graph extraction, and so on. But there's all kinds of predictions that one's making where there's dependencies between the predictions. And I really like this quote by Dan Roth. He says, "All interesting decisions are structured, so there's all kinds of crazy dependencies between things." But I think a lot of our machine learning algorithms take this nicely structured data and we essentially kind of flatten it and put it into this kind of matrix form, and that's convenient for our algorithms and so on. But I think there's a bunch of different issues with this, and the fundamental issue is oftentimes you're making an actually incorrect independence assumption. But then further, in the context of the structure and the outputs, you're not able to do the collective reasoning about the predictions you make for different entries in this matrix. And you're also, oftentimes when you do this flattening, you're doing all this kind of crazy feature engineering where you're kind of constructing features and those are the attributes that go in your table. And oftentimes you lose that when you later try and reproduce your methods and so on. So there's a real need to have ways that you can kind of declaratively talk about how you transform the structure into features. And so in this talk, I hope to provide you with some patterns, some tools, and some templates for dealing with these kinds of structure in both inputs and outputs. And as I go through these, I really hope that you'll keep in mind, for the kinds of problems that you're looking at, is there structure? If there is structure, are you exploiting it? And if you're not, could you? So the topics that I'm going to go over are, first off, some really, really, really basic patterns for doing structured kinds of problems. And these are naively simple, but we found over and over again that if you encode these little simple patterns, you can increase performance, usually a couple percentage points, but oftentimes 5 or 10 percentage points. So these are good tools for you to have. Or patterns for you to have. Then I'm going to go into tools. And for the tools, here I'm actually going to get into a little bit of technical detail about some work that we've been doing, some cool equivalences that we've found across different areas, and how these can make doing these structured kinds of problems tractable. So this is cool. And then at the end, I'm going to be talking about some bigger templates that build on these patterns to do kind of interesting problems in computational social science, knowledge discovery, and also touching on responsible data science and machine learning. So for the patterns, so how am I going to capture the structure? I'm going to use logical rules. These have advantages. They give you an easy way of talking about entities and links between entities. They tend to be interpretable. People like looking at rules. And bear with me if you're already saying, like, logical rules. Brendan yesterday said logical rules were terrible. I'm going to show you how to actually get them to work in the second part of the talk. But the patterns that I'm going to go over for structured prediction problems are really these kind of basic graphy problems where I'm trying to either predict labels for nodes in a graph, I'm trying to predict links between things, and I'm also trying to figure out when two things are the same. And let me just dive into the first one, collective classification, which is simply inferring the labels of nodes in a graph. And the little pattern for this, expressing this as logical rules, is super simple. It just says, okay, I'm going to use some local information that I have about the node. I'm going to make a prediction for the label based on that, but then I'm also going to use the structure. So if I have another node that's linked to it that has a label, I'm going to use that to infer the label for the node. And how can you tell that this is a collective or structured problem? If you look, the thing that I'm trying to predict, the label, occurs on both sides of the rule. So there's going to be a dependency between the different ways that I predict the labels. And, let me ground this in a really simple toy problem. This is a problem where I have a social network. I'm trying to infer some label. In this case, political label, but you can think of any kind of binary classification problem on a network. And usually in these problems, what happens is you have some labels given, and then you have some set that are unknown that you're trying to predict. And you want to do this in kind of a joint way. So how do we express this as rules? We're going to have some local rules, and these local rules can be things like, okay, if they donate to a particular party, then they're going to vote for that party. Or if they use a political slogan that's associated with some party, they're going to vote for a party. But more interestingly, we have these kind of structured rules where we say, okay, if your friend votes for a party, you're going to vote for a party. If your spouse votes for a party, you're going to vote for the party, and so on. So super simple, but it's surprising. You add these kinds of rules to a flat classifier, and oftentimes you get significant improvement in performance. The next pattern that I want to talk about is something with predicting links or edges in a graph. And for this, again, we have a really simple logical pattern that we can encode, which is that if I have a link between x and y, and there's some other variable z that's similar to y, then I should have a link between x and z. So first off, you can see, again, that it's collective because I have the thing that I'm trying to infer, which is the link on both sides of the rule. A simple example of this grounded in a kind of recommender system inspired setting where I have users, I have items, I have whether or not a user liked an item, and then I can have a rule that says basically if a user likes an item, there's another item that's similar to it, the user will like that second item. Conversely, I can also say, well, if a user likes an item, there's another user that's like that user, then that user will like an item. And I hope you get a sense here where there's this dependency that's going to happen between the links that you infer. By the fact that you infer one link, it's going to give you information about other links. And the third pattern that I want to describe is entity resolution. So entity resolution is the problem of figuring out when two nodes refer to the same underlying entity. And the pattern for this, again, we use some local information in terms of how similar things are, how similar their names are, how similar their structure is. But then the interesting thing is there's kind of two different settings in terms of the collective rules that you can have. One is a kind of transitivity, where I'm saying, well, if X and Y are the same and Y and Z are the same, then X and Z are the same. That works in some domains, but in other domains, you actually have a kind of matching problem. And so you see that there's this dependence on both sides of the rule, where it's slightly different, where you say, well, if X and Y match and Y and Z are different, then X and Z can't match. So this is a little bit more matching kind of problem that says I can only match to one thing. And again, in some domains, this is an appropriate structure to have. So these are super simple patterns. They buy you a lot, but I actually really like the case where you put all of them together and you have these kind of crazy, loopy kinds of graphs. And I'm going to be talking about those and talking about how you get those to work later in the talk. But I frame this all as logical rules. And logical rules have advantages, but they also have major disadvantages. So the disadvantages is dealing with them is intractable. As soon as you have like one inconsistency, everything falls apart. And then on top of it, I talked a lot about similarities. And, encoding that as a binary predicate, 0, 1, doesn't work very well. And so it's really nice to be able to have the ability to represent these. So I'm going to talk about some tools for actually really getting these patterns to work. And the tools come from the statistical relational learning community. There was a tutorial on Monday on statistical relational AI. There was also a tutorial on probabilistic programming. So it's coming from this world, building on this. There's been a lot of different languages proposed, and we're going to be adding one to the mix called PSL. What does PSL stand for? PSL stands for Probabilistic Logic Programming, and it's a declarative language for expressing these collective inference kinds of problems. The key reference is this recent JMLR paper that goes into way more detail than I'm going to be able to go into here. This URL has a code. It's open source, downloadable. There's tutorials, data sets, and so on. But the basic idea is that we're going to take these logical rules and assign weights to them. And this is just like a bunch of other languages, most notably Markov Logic Network coming out of Pedro Dominguez's group. We're going to use this to define a distribution over the unknown variables. But then the place where PSL differs is we're going to make the random variables continuous valued. And I'm going to explain 3 different semantics for why we end up doing that. And then the cool thing is we're able to make doing logical inference tractable. And this work allows us to take these disadvantages and turn them into advantages. So now we have a tractable way of doing things. we can deal with inconsistencies, and on top of it, as you'll see, we can represent similarities. So the foundations for this are very much some nice work by my former PhD student, Stephen Bach, who happens to be on the academic market. He also is one of the co-organizers of Saturday's workshop on learning from limited data. But fundamental to his results are kind of mapping the logical rules to concave functions and turning this into a concave maximization problem. And I'm going to unpack this for you, but for right now, try and kind of imprint this formula on your brain. We're going to see it a couple more times in the next few minutes. And the nice thing is we have semantics from 3 different worlds. One is coming from the theoretical computer science community and randomized algorithms. One of them is coming from the machine learning and statistics world around graphical models. And then the third is coming from the AI community around soft logic. So let me start with the first one in randomized algorithms. So in this setting, we have our weighted rules. So we have these non-negative weights, and we've turned the expression of the rules into clausal form. And we've introduced an index that goes over the positive literals and the negative literals. And now weighted maxat is the classic problem where you attempt to find the assignment to the random variables that maximizes the weights of the satisfied rules. Awesome. Except for this is NP hard. So there's very nice work from the randomized algorithms community where they convert this combinatorial optimization to a continuous optimization by introducing random variables which denote rounding probabilities. And these rounding probabilities are the probability that you round up to 1 or down to 0. And then there's this nice result from 1994 where they expressed the expectation for this optimization, and then they introduced a linear bound on this optimization. And the cool thing is they also were able to show an approximation guarantee that the continuous solution to the linear program, if you did a simple technique for turning it into a discrete solution, gives you a 3/4 optimal solution. So awesome. And if you paid attention and memorized that formula from a couple slides ago, this has exactly the form that I showed earlier. So cool. Now we go to a different community, the graphical models community. And in the graphical models community, we can represent our problem as a factor graph where you have random variables. And now the rules are essentially the potential functions. And this represents a Markov random field. The distribution for this is kind of the standard way of expressing this distribution in the factor graph. And then to do map inference, it's simply to find the assignment to the random variables that maximizes the probability. So we have this form. The only problem is, of course, this is NP hard too. So we're going to turn to approximation techniques to solve it. And we're going to use variational inference where we introduce mu's that are the marginals for the variables. We can then express a solution if we can find a globally consistent assignment for these marginals. The only problem is you can express it as a linear program, but there's an exponential number of constraints. So we'll use techniques from the graphical models community, particularly local consistency relaxations, to convert this to a simpler problem. And there's been a ton of work in this space. These are some of the kind of key original papers here. But the basic idea is you have this complex polytope. I'm going to relax the constraints. So we're going to do exactly the same thing here. And we're going to do it by introducing these pseudo-marginals, local pseudo-marginals. We'll express our optimization as before. And then what Steve was able to show, together with former postdoc Bert Wong, is by making use of the KT conditions, we can optimize out the thetas. We can project this into a simpler form for the objective. And if you look at this, it turns out to be exactly the same form we saw before. And they actually did a bunch of work comparing to other kind of LCR methods, dual decomp, and so on, and in some particularly loopy problems showed a lot of benefit from doing this. So these are two approaches where I get the same convex problem. The third approach comes from soft logic. In soft logic, what we do is we have random variables that denote degree of truth or similarity, which I said was going to be useful. There's a bunch of work on different ways of expressing these kind of Boolean expressions in these logics. The one that we're going to use that ends up being quite convenient is something called Lukasiewicz logic, which defines these operators as follows. And with a little bit of algebraic manipulation, we get out a max-sat objective where we can solve this exactly, in this case, using this convex optimization. And one way to interpret this is basically this term here is, we have these clauses. I'm adding up the truth values, and either the clause is satisfied, so it's 1, or there's some sort of amount of satisfaction, and essentially I'm trying to minimize the amount of dissatisfaction in the rules. And so again, this ends up giving me the same form. So the really cool thing about this is 3 very, very different interpretations. You get out the same convex optimization, and it gives you a way of scalably dealing with logic, probability, and similarity. So I think this is cool. I think it's actually kind of the tip of the iceberg. I think there's lots more to do here. But going beyond this, we introduce a notion of hinge loss Markov random fields. Just add some bells and whistles to the language. Now we allow arbitrary linear potentials. We also allow hard constraints. We allow squared hinges. And the general form looks kind of similar, but it's still convex. A PSL program looks something like this. So this is a program from the collective classification that I described earlier. And PSL essentially takes one of these programs, takes some input data, and defines a convex optimization. But now we can make it even faster. This kind of MRF actually has a lot of fine-grained structure. And so by looking at this fine-grained structure, we can actually improve our optimization techniques even more. And we used optimization technique ADMM in order to do this, but basically the idea is you solve these little sub-problems independently, you combine the results, and it's guaranteed to converge for convex problems. The only trick in doing this for PSL is how do you take the potentials and solve them quickly? And it turns out the potentials have this nice form where you can decompose it further. And it turns out if you go this far in decomposing the problem, you actually get these really simplified algorithms and programs, optimization programs. And so if we compare this to an off-the-shelf optimizer like CVX Pi, kind of industrial strength optimizer like MOSEC versus our PSL ADMM, we're just blowing it out of the water. This graph is at a scale that you can't really even interpret it. For example, a problem that has 150,000 potentials, it takes like 3 hours using CVX-Pi, it takes like 3 minutes using MOSEC, and it takes like seconds with ADMM, our implementation. And with PSL, we can do something that has 800 million potentials in less than a minute. So that's great. It's fast, but it can be fast and not be very accurate. So how well does it do? Here's some sample results across. This is an activity recognition problem, computer vision kind of problem. And this is an example of many of our results where you start off with just a really dumb, simple approach, add in a little bit of structure, and you get significant improvements in performance. Comparing to discrete MRFs, we can solve them as well, but we can do it way faster. Across a collective classification and link prediction task. And for something where you're really reasoning about similarities, so this is for drug-target interaction prediction, a comp bio kind of problem, we're able to do something that beats state of the art. But I think the most interesting thing about this work is that it gives a way of extending it. So if you have more information, it's easy to go from here. So to summarize PSL, it's fast. We can make it extra fast using smart optimization techniques. I haven't talked about it here, but we do have methods for learning the weights and also methods for dealing with latent variables, which changes the problem. And as I said before, it's open source, and you can get all the information here. I want to turn now to these templates. So now I hope I've convinced you that we have a way of solving these problems. But let's go back to our patterns and develop kind of bigger kinds of structured problems. And I'm going to do this across 3 different areas. So the first one is computational social science. I think this is a really interesting area where there's a lot of opportunities for structure prediction kinds of approaches. And the first setting that I want to go over is some work by my senior PhD student, Danya Sridhar, where we were looking at stance classification in online debates. And here we have a topic, climate change, related to the first invited talk. We have these people that are posting on it, and we can use information in the text to figure out, are they pro or anti the topic. But we can also use information about the dialogue and the discourse. So people are agreeing with each other, they're disagreeing with each other. And the cool thing is we can encode this as a PSL model in a really simple way. This builds on our collective classification example from the beginning, where we have local classifiers that try and predict, first off, the stance of a post, and second off, for an exchange, is it an agreement or a disagreement kind of exchange? And then we can do some reasoning where we say, okay, if someone posts something and it's pro and someone disagrees with that, then that person's post is anti. If someone posts something and they're pro and they agree, then that post is pro. And similarly, we can do this kind of reasoning with the agreement and disagreement links. And we get out something where we compare to a simple just text-based classifier, and we get a significant bump up in accuracy just by adding in these kind of really simple kinds of potential functions. The next computational social science problem that I want to go over is one around predicting links. So predicting trust links in particular. And the thing that I like about this work is we're able to actually model two different theories that are coming from the social science world about how trust links form. And one of these is structural balance, where this is the idea that, well, a friend of a friend is a friend, and an enemy of an enemy is a friend, and so on, and they have all these different valences for the pluses and minuses, the trust and distrust that are encoded in this theory. So we can represent this in an easy way as a PSL program. But then the second model that comes from the literature is something called social status. And this is when you're in kind of a more hierarchical setting where you kind of look up to the people above you on the hierarchy and you distrust the people below you in the hierarchy. So in this model, you have if A trusts B and B trusts C, then C doesn't trust A. And again, you have some collection of different valences for these triangles. But the cool thing is it's really easy to encode this as a PSL model. And this is work that Bert Wong, former postdoc, led, where we compared to existing approaches in the literature, and both of the PSL approaches did significantly better. But then the cool thing that we did next, which I think happens in a lot of computational social science kinds of problems, is we could add in a latent variable. And this latent variable has totally reasonable semantics. And we're going to say how trusting or how trustworthy is an individual. And we can, encode this. Then we add this to our model, and this totally blows away all the other models. So this simple thing of introducing latent variables in a smart way and then kind of making use of the structural constraints and then evaluating it on structure, I think, is a common pattern. So we've done a lot of other things in computational social science. I just want to call out briefly some nice work by Arti Ramesh on modeling engagement in MOOCs, some work by P. Kuki on hybrid recommender systems and explanations, and then finally some work by Sabina Tompkins that she's going to be presenting at a NIPS workshop on Saturday on cyberbullying. And so I'm excited about this space. I'm really happy to talk to folks afterwards if you are interested in trying to model things in this space. But let me turn to a really different kind of setting, but again, where I think structure and making use of these patterns really pays off. And this is in knowledge discovery or knowledge graph construction. And this is work that is very much driven by my former PhD student, Jay Pujara, who also happens to be on the academic job market. And he is also one of the co-organizers of the AKBC workshop that's on Friday. And so if you want to know more about this topic, I'm just going to go briefly into it, but definitely go to this workshop to find out more. But the basic idea is that we have these techniques, these information extractors that can extract out facts from the web and from other online sources. And these facts can be facts about entities, they can be facts about relationships, but the extractors are usually really noisy. And so how do you reason about them collectively to figure out which are the facts that you want to actually add into your knowledge base? And the cool thing is that we can actually use exactly the patterns that we gave at the very beginning, this kind of collective classification, this link prediction, this entity resolution, all are super important in constructing the knowledge graph. But then on top of it, we can use ontological constraints. And ontological constraints are things like subsumption relationships, mutual exclusion relationships are super useful. But the classic things for dealing with ontological constraints are intractable. And so we're going to use probabilistic soft logic to kind of make this inference, but make it tractable. And then on top of it, we can make use of extractor confidences and throw that into the model as well. So we can use PSL to make this tractable, and the PSL program looks something like this. And this is very much building on some work that Daniel Loud et al. Had done using MLNs for doing this. But the program is quite simple in terms of capturing ontological constraints, capturing entity resolution constraints, capturing other kinds of things about the extractor confidences. And he evaluated this on 3 real-world knowledge graphs, pretty large size. Some of these were knowledge graph constructions, and the last one with free brace is actually a linking problem, so you're trying to match across these databases. But to summarize the results, he was able to show that kind of across these 3 different settings, using each of the aspects of structure prediction that I talked about, we can improve performance. And that's great, but we can do it fast. So we can do this in a way that takes a few minutes to do it, even over these really large knowledge graphs. Then going to a different kind of setting where there's been a lot of work on embeddings. These have been shown to work really well, and particularly well when you have a lot of data. But we compared applying them in a setting where you have more noisy data, more sparse data, and found that our PSL methods really helped. Even baseline methods were doing better than the embedding methods. And I think this is really just a hint at how do we combine these kind of settings where you have embedding methods that work well versus structure methods when you don't have as much data, and so on. And I think this is an interesting area for further work. So the last thing that I want to touch on is actually a quite different interpretation of structure. And this goes into the area of responsible machine learning and kind of connecting to, there was yesterday's talk on bias, there were tutorials on fairness, but it's the perils of ignoring structure and the perils of ignoring structure actually in your domain. And the easiest case to start with is privacy. So a lot of the work in privacy says, oh, in order to be safe, just make sure you hide all your attributes and then you'll be fine. Well, if you're linked to people that happen to be exhibitionists that tell everything, then you're not going to be very private. They can leak a lot of information. There's actually some nice work by my former PhD student, Elena Zaliva, who looked at this setting. And we all kind of get the sense that you'll leak information from the people that you're linked to. But what she showed is that actually the groups that you're a membership of leak a lot more information. And oftentimes that's something that you don't even have control over hiding. So this notion of how does this structure impact the information that's leaked about you and who controls access to that information, I think is really interesting. And thinking about it from a structured perspective is important. The other area is around fairness. And this is a topic that's receiving a lot of attention now, which is great. But I think there's something that's missing in it, which is understanding the structure. And the structure is often something that's outside the data. So the structure can be either something that is in the organization or in the socioeconomic structure. And being able to be cognizant of this when you're doing your modeling and having a way of expressing it is important. And my current postdoc, Gulnush Farnadi, has some initial work where we've been able to encode these fairness constraints as something in PSL, where you can then make sure you obey those constraints and then do the optimization for learning in that setting. And the final place where I think there's real opportunity to make use of structure and really understand things is in this notion of algorithmic discrimination. And the fundamental structural pattern there is that there's some feedback loop. And the feedback loop is something like the rich get richer and the poor get poorer and so on. So having a way of encoding that, I think, is important. And understanding the structure can end up being the key to kind of mitigating some of the negative effects in these kinds of settings. So in closing, let me do the most important part of the talk, which is acknowledgments. I have an awesome group of students. I have a terrific collection of collaborators. And I'm lucky enough to have wonderful sponsors and a lot of great companies that I've worked with. I personally think that's one of the best things about being in this area, all the cool people that you get to work with. As far as the unreasonable effectiveness of structure, I've kind of come at it. I hope I've given you the perspective that there are ways of exploiting structure that can be tractable. But really, I think what we want to do as AI and machine learning folks is kind of complete the loop and really kind of being able to build on our approaches, discover structure, exploit structure, find new structure, and so on. And I think there's a real opportunity in this space. And I hope that I've kind of given you some ideas. So ideas for different ways in which you can exploit structure, different ways in which you can use it effectively. Like I said in the last slide, I think kind of there's this opportunity for combining unstructured and structured. But there's also these opportunities in combining logical and probabilistic, or as you saw, combinatorial optimization and continuous optimization. And then finally, from an AI perspective, there's this opportunity to be both data-driven and knowledge-driven, but doing that in kind of a coherent way that ends up being also tractable. And I think there's tons of cool applications across all kinds of areas, and this is a real space for opportunities. So, thank you.
Thanks for a great talk. We have some time for questions. If you'd like to ask questions, please line up near the microphones and please speak into the microphones. There's a question there.
Thank you for a great talk. Question, how do you handle situations when there is a structure, but you don't know exactly what kind? For example, you're predicting sales of various products and there is cannibalization effect, but you don't know to what degree, how strong, and between which entities.
So I'm sorry, I couldn't hear. I heard the gist of your question, but not the particular.
Sure. So how do you handle situations when there is a structure, but you don't know the exact nature of the structure? For example, you have a deep learning model that predicts sales of products, and there's cannibalization effect. You introduce new product that affects another, but you don't know how much. So how do you handle that?
So I think there are approaches where you can encode something about, so either it's completely unstructured and you need to kind of map this kind of unstructured thing you discovered into some form of semantics. And I think that's an interesting area, but not one that I know how to do or have really looked at. I do think that there's an opportunity, though, in kind of structuring the model of kind of making use of something that you know about the domain, something that you know about the entities and so on. And I didn't quite catch the part about the particular thing that you were worried about in terms of the evaluation of it. So.
Let's say that you sell 3 products and you're thinking of introducing a new one. Mm-hmm. And there is similarity between products, but you're not exactly sure how to measure it. And you are concerned that you introduce a new product and your other product sales go down as a result. And you're trying to figure out, do I predict individually for each product, or do I create some sort of a rule that this affects that, but you don't know how much and what affects what?
Yeah, so the assignment problem. So in this setting, I think that you could kind of look at different models that are making either introducing some more structure into the similarity, corresponding to product classes and so on, and compare performance. But exactly how you would do that and make sure that it was comparable across the models is non-trivial.
Thank you.
There's a question here on this side.
Yep.
Hello. Okay. Thanks, Professor, for a great talk. I have a question concerning this probabilistic soft logic, which seems to be reminiscent of fuzzy logic. So my first question is about, would you please elaborate, what's the difference from the fuzzy logic?
Actually, so this is interesting, and the term soft is coming from fuzzy logic. So we are using a particular interpretation for the rules that comes from soft logic. But then the place where there's a huge difference between what we're doing and what fuzzy logic traditionally does for doing inference is we take this interpretation and then we put it into a probabilistic model. So we put it into a graphical model. And so there's a piece that we're using that is the same, which is the Lukashevitz logic. But then the way that we actually do inference is different.
It's okay asking one more question, just one more. So what's the connection now about this PS software logic to deep learning? Do you see any kinds of opportunity to explore the connection between these two?
Yeah, so in terms of the connection, I think there is kind of a superficial answer to this, which I still think is promising and interesting, which is you can combine the two in reasonable ways. There's a deeper connection if you really look at the kind of form that we're optimizing and try and kind of push that in and make analogies between deep learning. And this is something that actually I've talked with Vichy about. So I think there's opportunities there as well for actually a deeper technical connection between the two. And it's not surprising that there would be.
Is there a question there?
Thanks for the talk. I had a question. So let's say you have like a set of rules, and you're about to add an extra rule. So they're like kind of 3 cases. This rule like doesn't give you any new information. It doesn't change any assignment of your labels or anything. This rule is like helpful. It improves your prediction in some cases. And there's the like third type of rule, which is maybe it makes your whole optimization problem super hard. Or maybe it's like wrong or anything. So is there any way we could, get to, define which rules are helpful or reject some rules?
Yeah, so definitely one thing that I didn't talk about is simply the weight learning, where you can figure out, which rules and what weight should they have. But a bigger thing is what model selection or actually structure learning is what it's often called, where you actually learn the structure of the rules. And for that, there are some existing techniques that I think you could just directly port over to PSL. But I think there's opportunities for doing things that are even more interesting, where you actually have kind of a meta PSL program that learns the structure of the PSL model, and that's something that we're actually working on in the context of causal models. So, but it's an important problem.
We have a question here, and I'm afraid in the interest of time, that will be the last question that we can take.
Well, thank you for a great talk. I just wanted to ask a clarifying question. You said that the potential functions, they decompose, but you didn't say much about the complexity of the rules. Is there a specific family of rules we have to stick to in order for the potential functions to decompose? How complex rules can we incorporate?
Yeah, sorry, I probably went over that too fast. So the form for the potential functions is very specific. It's this kind of hinge loss kind of thing. So they're convex, and they have they're linear in that sense. And so a lot of what I was doing at the beginning was all around how do you take a potential function that's expressed as a logical rule and then convert it to this hinge loss. But yeah, there's a restriction that you're going to have these, and that's the place where you get the tractability from.
So I cannot. So if it's products or any other form, I cannot use this technique.
So the general technique works when you have these convex things, and then we've done some things that are specific to the particular form. So you'd have to kind of look.
I have to massage it in.
But yeah, it's very much a choice, not surprisingly, to get it to be that tractable.
Thank you.
Let's thank the speaker once again.